So we're going to uncover the process of solving a first-order linear differential equation. So first of all, what do these things mean? Well, the order of a differential equation denotes the highest derivative that is found inside the equation. In this case, we're focusing only on differential equations that have the first derivative. The concept of linear is a little bit confusing because what we mean by linear is we mean linear with respect to y. So here is the general structure of a first-order linear differential equation. So you can see the first-order component here, and the linear component falls into play here. If you think about it, it's linear with respect to y, and it kind of has this form, y equals mx plus b. And I say kind of because the slope in this case and the x in this case, they're components of this equation, but it kind of has that linear format. Again, linear in terms of y. So what are some examples? Some examples that we can look at that would be probably most evident. dy dt equals, let's say, t squared plus 5 parentheses times y plus sine of t. So this is a first order linear because we can identify these components. Now a of t is just some function of time, and so the function of time, again, doesn't have to be linear. It has to be linear with respect to y. And this component here would be what we would call b of t. Another case would be a situation in which perhaps one or both a of t would be 0. For example, 0.2y, which is a homogeneous differential equation, is such that if you write a plus 0 there, a of t equals 0.2 and b of t is equal to 0. So if b of t is 0, this has a special name. B of t equals 0 means we call the differential equation homogeneous. And if b of t is not equal to 0, then we call the differential equation non-homogeneous. And another case would be, for example, a first course in integral calculus. We might have something like this. We might see a function like 3t. Well, we can use Calc 2 techniques to integrate that, but as it turns out, this can be rewritten in a linear form, 0 times y plus 3t, where a of t is 0 and b of t is 3t. So what strategy do we have to try to solve this equation where maybe we have a non-homogeneous differential equation? So it requires a product rule trick, which seems strange to bring back the rule for taking derivatives into a class in which we're essentially using integrals. Now the product rule states that the derivative of a product of two functions of time, f and g, is the product of the derivative of one times the other unchanged plus the first function times the derivative of the second. And the way we're going to use this is we are actually going to manipulate our equation to get that, and then we're going to work backwards and we're going to replace it with the derivative of f times g. So we're going to notationally replace this with this component over here. Alright, so the first step in even seeing that the product rule might apply is rewriting the differential equation, moving over the a of ty term to the left-hand side. Okay, so if we do this, for this particular example, we get dy dt minus 3y equals 2t. Moreover, I'm actually going to write this as plus negative 3y, so I kind of have already the f prime g plus f g prime notation. Okay, well, if you stare carefully at this, you'll notice that the first term right here is sort of, or as if, this guy, maybe we could call this f prime, and then f is the original function, the non-differentiated version, and our problem comes into play here. We do not have a g or a g prime, and we cannot call g prime negative 3, primarily because that would imply that the coefficient of dy dt, which is right now just a 1, the derivative of 1 is not equal to negative 3. G and g prime have to be integrals and derivatives with respect to one another. That is, g differentiated should give me g prime, and g prime integrated should give me g. That's simply not the case right now. So the question is, how do we introduce the missing pieces? How do we get a function in here such that when we take its derivative, we get the function that's out in front here? Can we simply add terms? Well, not if I want to have multipliers. I want to make sure that I have g times f prime. So can I multiply? As long as I multiply both sides by the exact same quantity, I will leave the sides unchanged. So what we're going to do is we're going to try to create this factor that we're going to call mu of t generically here. And what I'm going to attempt to do is I'm going to multiply through by this factor on both sides so that I keep the balance the same. And I'm going to just simply write mu of t as mu. I'll keep in mind that it's a function of t. And when I multiply both sides by it, what I now have is mu times dy dt plus negative 3 mu times y is equal to 2 times mu times t. All right, well now if I look at the structure once again, what I will notice is that I have the form g times f prime plus g prime times f. Okay, well I already have identified dy dt as f prime. I've identified y as f. So that means everything else in front of dy dt must be part of g, and everything in front of f must be part of g prime. Okay, so I have the product rule type formula. I haven't violated any algebraic laws. Everything is still algebraically precise. But the question is, what do we do with this? We don't know what mu of t is. However, there's a careful relationship here to notice. That is, we do know that if I take the derivative of g, I should get g prime. Well, that translates over into, we've identified g as being mu, and I've identified g prime as being negative 3 mu. And so what I'm left with here is I have to find a function such that when I take its derivative, I get negative 3 times itself. Well, in the back of our minds, we should be thinking that mu is exponential. Only an exponential function is going to have its derivative involve that same original function. Well, here's how we could do this. How we could actually derive this mathematically. Well, the derivative of mu with respect to t can be also written this way. d mu dt equals negative 3 mu. Now, I notice that my dependent variable in this new differential equation I formed is actually makes this equation homogeneous. So I can solve this by separation, and I will do that. So I get 1 over mu d mu equals negative 3 dt. And if I integrate both sides, I'm left with natural log of mu must equal negative 3t. Now I won't add a plus c on here because this is just something I'm multiplying through by. I could just say, you know what, I'm going to let c equal 0. It does not matter. It's just a factor that we're going to use to multiply through by. And when we integrate later on, that integrating that integration will result in getting our arbitrary constant that we need for the solution. So I'm going to exponentiate both sides, and I get mu is equal to e to the negative 3t. And in fact, that is an exponential function. And if I take its derivative, I get negative 3 e to the negative 3t. That is, if I take the derivative of e to the negative 3t, then I'm going to get 3e to the negative 3t. So the function and its derivative both involve the use of e to the negative 3t. So I now know mu. How do I proceed with this? Well, now I can go ahead and condense and isolate y of t. So at the last step, we knew the following. We knew that mu times dy dt plus negative 3 mu y has to equal 2 times mu times t. And now I know that mu is e to the negative 3t, so I'll plug that in, plus negative 3e to the negative 3t times y equals 2e to the negative 3t times t. All right, so that gives me that component. Now I've already identified that this is G. This is F prime. This is G prime, and this is F. And so I now have the product rule. So G is equal to e to the negative 3t. F is equal to y, which means that this whole component here, if I now convert it into the left-hand side of the product rule, is exactly the derivative of G times F. In other words, F times G is y times e to the negative 3t. So I've just condensed that whole left side into the derivative of y times e to the negative 3t. And what I have left is 2t e to the negative 3t on that side. And here's the beauty. Our whole goal is to integrate away any dy dt's. Well, I guess there's the derivative of y times e to the negative 3t, but I don't have any dy dt's left. So here is why we wanted the product rule. If I now proceed to integrate both sides with respect to t, on this side and this side, then the integral of the derivative function is simply the function itself. If I take a derivative of y e to the negative 3t, and then I take its integral, I end up with the original function back. So I didn't have to do any work on this, on integrating this. It was simply a cancellation of the integral and derivative. They're essentially inverse operators. And on this side, I have to work a little bit more. I have to integrate 2t e to the negative 3t. And using an integral sheet, I have that integral of something to the form x times e to the ax dx is equal to this thing on the right. So I will go ahead and grab this so we can paste it in. And so here's the form of the integral that I want to take, and I'm applying it to this right-hand side. I am going to actually write this as 2 times the integral of t e to the negative 3t dt. And I can identify the components. I see a, and I see my a right there. And instead of using x, I'm going to use t. So the integral of this is going to be quantity t over a, which is negative 3, minus 1 over a squared, which is negative 3 squared is 9, times e to the negative 3t, e to the negative ax. And then, of course, I need my plus c term on here because now I am actually solving the differential equation and I need that arbitrary constant. So over here, I will actually write the final solution now. All that's left is I have to divide both sides by e to the negative 3t, and I get y is equal to, let's see, well, e to the negative 3t divided by e to the negative 3t will just leave me what's in parentheses, which is t over 3 minus 1/9. But I have to divide the constant. This is a variable expression, so I have to divide the constant by that. So I get plus c over e to the negative 3t, or more generally, y equals c e to the positive 3t plus 1/3 t minus 1/9. And we're done. We now have a function for y. So let's look at a more general version of this now. What if a of t and b of t are just some general functions? Well, the way I'll proceed is much in the same way. I will move over the a of ty term, and I'm just going to leave a of t and b of t alone. Next, I'm going to multiply by some integrating factor that we're going to call mu on both sides. And so that leaves me with mu times dy dt plus negative a of t times mu times y equals mu times b of t. All right. Well, again, I'm going to do my identification here. And my identification is that this is f prime. This must thereby be g. Over here, I've got my f, which means that this whole component must be g prime. Okay, so it looks more complicated, but our same logic applies. The derivative of g must equal g prime, which means that the derivative of mu must equal negative a of t mu. And now we can go ahead and proceed in a very similar fashion. So the beauty here is that I have everything in terms of generic a of t's, b of t's, and mu's. So what I'll go ahead and do now is I will write the left-hand side once again as d mu dt, just so for that visual effect, and I have minus a of t times mu here. Now again, this is an exponential based function. The only function whose derivative I can take and get some multiplier times the original function involves an exponential. So I'll solve this via separation of variables, and I have to be careful here because a of t is now a function. I don't know what structure a of t has. In other words, I don't know what a of t equals. So what I'll do is I'll get it as far as I can, and I'll once again move over mu, nothing different there, which is actually, if you think about this, this is where the exponential function comes from. And then I'll have negative a of t dt. And when I integrate both sides now, what I'm left with is the natural log of mu, once again, equals negative integral of a of t dt. That's as far as I can take that because, again, I don't know what a of t equals. So what I'll do now is exponentiate both sides, and I'll end up with this awkward looking thing that is e to the negative integral of a of t dt. So if you tell me what a of t is, I will be able to tell you what mu is. And that requires me to compute this integral, but it's a much shorter, faster process. So now we still have to handle all of this stuff here. Now we've got to convert into, oh, by the way, the mu of t function that we're creating here is called the integrating factor. Some people call this method the method of integrating factors. And so we know that now we're left with mu times dy dt plus negative a of t times mu times y, times y is equal to mu times b of t. And I already know what mu is, but once I have that, and I know again that this is g and this is f prime, and I know that what I have here is g prime and f, then what I'm now able to do is to rewrite this as the derivative of f times g is equal to mu times b of t. And what is f and what's g? Well, f is y, once again, and g is mu, once again. And so now I have the derivative of y times mu is equal to mu times b of t. Alright, well now I can integrate both sides with respect to t, and here's again why we do this. The integral of the derivative of y times mu, all with respect to t, is simply y times mu. And I can't really do anything there on the right, because I don't know what mu and b of t are. If I did know them, and supposing I could actually do the integral, then I would be able to compute the right-hand side. And my final step here is to solve for y, so I'll divide both sides by mu, or multiply by 1 over mu. Now I have to be careful. I cannot pass mu inside of that integral. I cannot pass mu inside of that integral because mu is a function of t, and the requirement was first to calculate the integral of mu times b of t. If you look back at our example, this is what we had to do first before we divided by mu of t. And so I'm left with my final solution. My final solution is this, and we'll just go ahead and state that as, given a differential equation that is first order linear, then the solution is y equals 1 over mu times the integral of mu times b of t. And I don't know why I'm writing b of t here. I could just say mu times b because we decided instead of writing mu of t each time, we just write mu. Again, mu is not a constant. Mu is a function of time. So if we're going to use t's, I suppose we should use them everywhere. Where, before you actually try to compute this, you must compute mu of t, which is equal to that derivation, e to the negative integral of a of t dt. So we have our first thing we need to compute, and then we can finally compute the solution. We've got to be careful to identify a of t here and b of t here when our equation is written in this form. So let's take a look at another situation. Suppose that we have dy dt equals, I don't know, we'll say t times y plus, we'll say plus 5 to keep this simple. Okay, so I know from identification that a of t is equal to the constant t, and sorry, not the constant, but the function t, and b of t is equal to the constant of 5. So mu of t is calculated by taking e to the negative integral of a of t, which is just t, with respect to t, and oh, actually, I'm gonna actually create a slight modification here for purposes we'll see in a second. In order to make this, it's really easy to make these non-integrable, meaning that you cannot actually come up with a closed form answer. So in this case, I will get, let's see, the integral of t is going to be 1/2 t squared. So I'll have e to the negative 1/2 t squared, and there's my mu of t. And I know that now I need to funnel this all into the y function, which is 1 over mu of t times the integral of mu of t times b of t dt. I know that mu is e to the negative 1/2 t squared, so 1 over that will be e to the positive 1/2 t squared. Again, 1 over e to the negative 1/2 t squared is e to the positive 1/2 t squared times the integral of e to the negative 1/2 t squared times b of t, which is 5t. And now the reason I chose to use 5t here is because by substitution I can now solve this integral out. And I will actually go ahead and pull up my integral sheet here. So let's see. We have something of the form. Let's see if we can identify this. There we go. We're starting to get at it. Okay. X e to the negative ax squared. Well, that's what we have. We know that the integral of x squared e to the negative ax squared. Oh, no, that's not the one we have. This is the one we have. Is negative 1 over 2a e to the negative ax squared. So the integral of this is going to be, let's see, a is, I'm going to write this out and make it a little bit easier. So the integral of x e to the negative ax squared equals, with respect to x, is, let's see, 1 over 2a e to the negative ax squared. Okay, so in our case, we have t, and if I factor out that 5, then I can write 5 times the integral of t e to the negative 1/2 t squared times our dt. And now I've got to be careful here because what I have here as negative a, my negative a is equal to negative 1/2. In other words, the coefficient of the squared term is negative 1/2. So this and this must be the same, which means a is actually equal to positive 1/2. And so that gives me, according to the right-hand side, I have 5 times 1 over twice a, which is 2 times 1/2, times e to the negative a x squared, which is negative 1/2 x squared. And of course I'm going to have a plus c on this, but we'll put that on there. So I get 1 over 2 times 1/2. Well, that's just going to be 5e to the negative 1/2 x squared plus c. And okay, now I can fill this in. So I have e to the 1/2 t squared times 5e to the negative 1/2 t squared. Should put a t there and a t there. Plus c. And when I distribute that in now, e to the 1/2 t squared, e to the negative 1/2 t squared cancel out. So that leaves me with 5. And e to the 1/2 t squared times c is going to be plus c e to the 1/2 t squared. And there's my solution. I have that y of t equals 5 plus c e to the 1/2 t squared. So you can see how much easier it is to use that technique. Still quite a bit of work to arrive at the algebraic solution, but because of our general form allows us to apply this quote-unquote quick method to any first-order linear differential equation.